Imagine a cosmic dance where not two, not three, but four stars whirl around each other in an intricate ballet of gravity and chaos. This isn't the stuff of science fiction, it's the reality of quadruple star systems, some of the most mysterious and fascinating structures in the universe. These systems defy our expectations, challenge our understanding of stellar mechanics, and hide secrets that could rewrite the rules of astronomy. What happens when four stars share the same cosmic stage? How do their gravitational forces interact, and could planets even exist in such extreme environments? In this video, we're diving deep into the strange and incredible world of quadruple star systems, uncovering 50 mind-bending discoveries that will leave you in awe. From planets orbiting four suns to systems with black holes lurking in the shadows, this is a journey through the cosmos like no other. So, buckle up, because by the end of this video, you'll see the night sky in a whole new light. Let's explore the mysteries of quadruple star systems together. Now, let's turn our attention to the very first quadruple star system ever discovered. Back in the early 20th century, astronomers were stunned when they stumbled upon a system where not one, not two, but four stars were locked in a gravitational embrace. This groundbreaking discovery took place in the constellation of Lyra, and it was named the Castor system. What made this find so extraordinary was that it completely upended the prevailing ideas about how stars could exist in the universe. At the time, most scientists believed that stars either orbited alone or in pairs, but the Castor system proved that nature had far more complexity in store. This system consists of two pairs of binary stars, each pair orbiting the other, creating a delicate and dynamic dance of gravity. Its discovery forced astronomers to rethink stellar mechanics and open the door to the study of more complex multi-star systems. The Castor system remains a cornerstone in our understanding of the cosmos, reminding us that the universe is always ready to surprise us. With this discovery, the stage was set for even more incredible revelations about quadruple star systems, and our journey through these cosmic mysteries is just beginning. Now, let's venture into the fascinating world of gravitational chaos within quadruple star systems. When four stars are bound together by gravity, their interactions create a cosmic ballet that is anything but orderly. Unlike systems with fewer stars, quadruple systems introduce an extra layer of complexity, with each star tugging on the others in unpredictable ways. This results in orbits that can shift dramatically over time, sometimes even leading to close encounters or ejections. A prime example of this chaos can be found in the system known as KIC 2,856,960, where the star's gravitational pulls create intricate and ever-changing patterns. Astronomers have observed that the orbits in this system are so unstable that predicting their future movements is nearly impossible. Another striking case is the HD 91,962 system, where the stars' paths are so intertwined that they resemble a tangled web rather than neat elliptical orbits. These chaotic dynamics not only challenge our understanding of gravity, but also raise intriguing questions about the long-term stability of such systems. By studying these gravitational puzzles, scientists are gaining new insights into the forces that shape the cosmos, reminding us once again that the universe thrives on complexity and surprise. As we continue our exploration, we'll uncover even more astonishing aspects of these multi-star wonders. Moving into another intriguing aspect of quadruple star systems, let's turn our attention to the remarkable discovery of planets within these chaotic stellar environments. At first glance, it might seem nearly impossible for planets to form and persist in systems with four stars, where gravitational forces are so intense and unpredictable. Yet, astronomers have uncovered several examples of planets that not only exist but also thrive in these extreme conditions. One such system is PH1, where a gas giant orbits a pair of binary stars which themselves are gravitationally tied to another distant pair. The planet in this system endures a complex dance of gravitational pulls, yet it maintains a stable orbit, defying expectations. Another fascinating case is Kepler 640, where a rocky planet orbits within the habitable zone of one star despite the chaotic influence of its three stellar companions. These discoveries challenge our understanding of planet formation and stability, suggesting that even in the most turbulent environments, planets can find a way to exist. The presence of such planets also opens up new possibilities in the search for habitable worlds, as it expands the range of environments where life might potentially emerge. By studying these planets, astronomers are gaining valuable insights into the resilience of planetary systems and the conditions necessary for their survival. This discovery reminds us that the universe is full of surprises and that even in the most unlikely places, the potential for life may still exist. Now, let's shift our focus to a system that truly embodies the elegance of cosmic choreography, HD 98800. This quadruple star system is often referred to as the dancing stars due to the mesmerizing orbital patterns of its four stellar components. Unlike many other multiple star systems, HD 98800 features two pairs of stars that orbit each other in a delicate, synchronized ballet. The stars in each pair are separated by a relatively small distance, creating a tight gravitational bond, while the two pairs themselves orbit a common center of mass at a much greater distance. This intricate setup results in a dynamic interplay of gravitational forces that keeps the stars in a constant state of motion, almost as if they are performing an endless cosmic dance. What makes HD 98800 particularly fascinating to astronomers is the way its stars' orbits are so precisely balanced. Despite the complexity of their movements, the stars manage to maintain a stable configuration over long periods, offering a rare opportunity to study the long-term behavior of multiple star systems. This system has become a key focus for researchers trying to understand how such complex gravitational interactions shape the evolution of stars and their surroundings. The dancing stars of HD 98800 serve as a reminder that even in the vastness of space, there is a kind of order and harmony that can emerge from chaos, inviting us to marvel at the intricate beauty of the universe. Moving on to another intriguing aspect of quadruple star systems, let's explore the mystery of uneven mass distribution. In some of these systems, the four stars can have vastly different masses, with one star being significantly heavier or lighter than the others. This imbalance isn't just a curiosity, it plays a crucial role in shaping the system's dynamics and evolution. When stars of different masses share the same gravitational space, their interactions become more complex. The more massive stars exert a stronger gravitational pull, which can disrupt the orbits of their lighter counterparts, leading to unpredictable changes over time. For example, in systems where one star is much more massive, it can dominate the gravitational field, causing the other stars to adjust their orbits or even be ejected from the system entirely. This uneven mass distribution also offers clues about how stars form. Astronomers believe that these imbalances may result from the way gas and dust collapse in stellar nurseries, with some regions accumulating more material than others. By studying these systems, scientists can piece together the puzzle of star formation, understanding why some stars grow to be giants while others remain relatively small. The presence of uneven masses in quadruple systems challenges our assumptions about balance and stability in the cosmos, reminding us that even in the orderly dance of the stars, there's always room for unexpected twists. This fascinating phenomenon not only deepens our understanding of stellar evolution, but also highlights the diversity and complexity of the universe. Now, let's venture into the shadowy depths of space where quadruple star systems take on an even more mysterious dimension, the presence of black holes. Yes, some quadruple systems don't just host stars, they also include these enigmatic cosmic giants. Black holes, regions of space where gravity is so intense that not even light can escape, add a layer of complexity to these already intricate systems. The formation of such systems is a puzzle in itself. One possibility is that a massive star within the quadruple system collapses at the end of its life, forming a black hole while remaining gravitationally bound to its stellar companions. Another scenario involves a black hole being captured by the system, drawn in by the group's collective gravity. Detecting black holes in these environments is no easy feat. Black holes are invisible by nature, so astronomers must rely on indirect methods, such as observing the gravitational effects they have on their stellar neighbors. For example, if a star in a quadruple system exhibits unusual orbital behavior, such as sudden speed changes or erratic paths, it could signal the presence of a hidden black hole. These systems challenge our ability to study black holes, as the gravitational interactions between four stars and a black hole create a chaotic dance that's difficult to decipher. Yet, they also offer a unique opportunity to explore the behavior of black holes in multi-star environments, shedding light on how these cosmic phenomena influence their surroundings. Quadruple systems with black holes remind us that the universe is full of surprises, pushing the boundaries of our understanding and inviting us to uncover the secrets lurking in the dark. Shifting our gaze to the life cycle of stars, quadruple star systems offer us a front-row seat to the grand spectacle of stellar evolution. These complex systems, with their intricate gravitational dances, provide a unique window into the processes of star birth, life, and death. When stars form in quadruple systems, their creation is often influenced by the gravitational pull of their siblings. This can lead to variations in size, mass, and even composition, giving astronomers a chance to study how stars develop under different conditions. As these stars age, their interactions become even more fascinating. The gravitational forces between four stars can cause them to exchange material, alter their orbits, or even trigger dramatic events like stellar collisions. This dynamic environment allows scientists to observe how stars evolve in ways that would be impossible in isolation or simpler systems. When a star in a quadruple system reaches the end of its life, its death can have profound effects on its companions. For instance, the explosion of a star as a supernova can eject material that may later form new stars or planets, or it can leave behind exotic remnants like neutron stars or black holes. Quadruple systems also challenge our understanding of stellar timelines. The gravitational chaos within these systems can accelerate or delay certain evolutionary processes, creating stars that defy conventional models. By studying these systems, astronomers can piece together the complex puzzle of how stars are born, live, and die, offering insights that extend far beyond the boundaries of quadruple systems themselves. This exploration not only deepens our knowledge of stellar evolution, but also highlights the interconnectedness of the cosmos, where the fates of stars are often woven together in ways we are only beginning to understand. Now, let's turn our attention to a system that defies expectations with its sheer speed. Among the most astonishing quadruple star systems discovered is one where the stars orbit each other at breakneck velocities. In this system, the stars complete their orbits in a fraction of the time it takes in more typical systems, creating a whirlwind of gravitational activity. These rapid orbits are not just a spectacle, they also challenge our understanding of gravity and the mechanics of stellar motion. When stars move at such high speeds, the gravitational forces between them become even more intense, leading to complex interactions that can alter their paths and behaviors in unpredictable ways. This system provides a unique testing ground for theories about how gravity operates in extreme environments, offering insights that could reshape our models of stellar dynamics. Additionally, the high orbital speeds can generate intense radiation and other energetic phenomena, giving astronomers a rare opportunity to study how such forces influence the evolution of stars and their surroundings. By observing this system, scientists can refine their understanding of the delicate balance between gravity, motion, and energy in the cosmos, revealing new layers of complexity in the dance of the stars. This discovery not only pushes the boundaries of our knowledge, but also highlights the incredible diversity of behaviors that quadruple star systems can exhibit. Moving forward, let's explore a fascinating feature found in some quadruple star systems, eclipsing binaries. In these systems, two of the four stars are paired in such a way that they periodically pass in front of each other from our perspective here on Earth. This creates a phenomenon known as an eclipse, where one star temporarily blocks the light of the other. These regular eclipses are not just a stunning cosmic event, they serve as a powerful tool for astronomers. By carefully measuring the changes in brightness during these eclipses, scientists can determine the sizes, masses, and even the shapes of the stars involved. Additionally, the timing of these eclipses provides crucial data about the stars' orbits, allowing astronomers to calculate their distances from each other with remarkable accuracy. This phenomenon is especially valuable in quadruple star systems because it offers a rare opportunity to study the properties of individual stars within such a complex arrangement. The precision of these measurements helps astronomers refine their models of stellar behavior and better understand the intricate dynamics at play in multi-star systems. Eclipsing binaries act as natural laboratories, revealing details about stars that would otherwise remain hidden. This discovery underscores how even the simplest interactions in the cosmos can unlock profound insights into the workings of the universe. Delving even deeper into the mysteries of quadruple star systems, we now turn our attention to the oldest known example of such a cosmic arrangement. This ancient system offers a unique window into the early universe, providing clues about how multiple star systems formed billions of years ago. Located in a distant corner of the cosmos, this quadruple star system is estimated to be over 12 billion years old, making it one of the earliest structures to emerge after the Big Bang. Its age suggests that the processes creating multiple star systems were already at work in the universe's infancy, challenging previous assumptions about the timeline of stellar formation. The stars in this system are also remarkably similar in mass and composition, hinting at a shared origin in a dense cloud of gas and dust. Studying this system helps astronomers piece together the conditions of the early universe, revealing how gravitational forces and turbulence shaped the first stars. Additionally, the survival of this system for such an immense period of time offers insights into the stability of quadruple star systems over cosmic timescales. By examining its dynamics, scientists can better understand how these systems evolve and persist, even in the face of the universe's chaotic forces. This discovery not only highlights the resilience of multiple star systems, but also underscores their role in the broader story of cosmic evolution. As we continue to explore these ancient systems, we uncover more about the origins of the stars that light up our universe today. Turning our gaze to the fascinating interplay of stars and their surroundings, we now explore quadruple star systems adorned with protoplanetary disks. These disks, often referred to as the cradles of planet formation, are vast rings of gas and dust that orbit young stars, providing the raw materials for planets to take shape. In the case of quadruple systems, the presence of four stars adds a layer of complexity to this process. The gravitational forces exerted by multiple stars can distort these disks, creating intricate patterns that challenge our understanding of how planets form. For instance, in some systems, the disks are stretched into elongated shapes, while in others, they are fragmented into distinct rings or spirals. These disruptions can slow down or even halt planet formation in certain regions while accelerating it in others. Yet, despite these challenges, planets do emerge in these chaotic environments, often in unexpected configurations. Some planets may orbit a single star, while others could traverse the gravitational fields of multiple stars, leading to highly unusual orbits. The study of these systems reveals the resilience of planet-forming processes, even in the face of extreme conditions. By analyzing how protoplanetary disks evolve in quadruple systems, astronomers gain valuable insights into the diversity of planetary systems across the universe. This discovery not only expands our understanding of planet formation, but also highlights the remarkable adaptability of cosmic processes in the face of complexity. As we continue to unravel these mysteries, we uncover more about the incredible variety of worlds that might exist beyond our solar system. Now, let's turn our attention to one of the most intriguing mysteries in quadruple star systems, the case of the missing star. In some systems, astronomers have observed only 3 stars despite strong evidence suggesting a 4th should be present. This puzzling phenomenon raises questions about what could have happened to these elusive celestial bodies. One theory suggests that the missing star may have been ejected from the system due to intense gravitational interactions. In chaotic multi-star systems, close encounters between stars can sometimes fling one out into space, leaving behind a trio where there was once a quartet. Another possibility is that the star collapsed into a black hole or neutron star, making it invisible to traditional detection methods. Alternatively, it could be obscured by thick clouds of dust or outshined by its brighter companions, rendering it nearly impossible to spot. Some researchers even propose that the missing star might have been torn apart in a violent collision or consumed by another star in the system. These theories not only challenge our understanding of stellar dynamics, but also push astronomers to develop new techniques for uncovering hidden stars. By unraveling the mystery of these missing stars, we gain deeper insights into the complex and often unpredictable nature of quadruple star systems. This discovery reminds us that even in the vastness of space, there are secrets waiting to be uncovered, and every star has a story to tell. Shifting our focus to the dramatic side of quadruple star systems, let's dive into those with explosive histories. Some of these systems have experienced supernova, the most powerful stellar explosions in the universe. When a star in a quadruple system goes supernova, the sheer force of the explosion can dramatically alter the dynamics of the system. For instance, the shock wave from a supernova can push other stars out of their orbits, creating new and often chaotic trajectories. In some cases, the explosion might even eject one or more stars from the system entirely, leaving behind a smaller group of survivors, but the effects don't stop there. Supernova also leave behind remnants such as neutron stars or black holes, which can significantly influence the system's future. Imagine a black hole forming in the midst of a quadruple system. Its immense gravitational pull can warp the orbits of the remaining stars and even consume material from its companions. Additionally, the explosion can trigger new star formation in the surrounding space, as shockwaves compress gas clouds and ignite the birth of new celestial bodies. These explosive events not only reshape the systems they occur in, but also provide astronomers with a unique window into the life cycles of stars. By studying these remnants and their impact, we gain a deeper understanding of how even the most violent events in the universe play a role in shaping the cosmos. The explosive histories of these quadruple systems remind us that space is a dynamic and ever-changing stage, where destruction and creation are intricately linked. Turning our gaze to the broader cosmos, let's examine the role quadruple star systems play in shaping galaxies themselves. These intricate stellar families don't just exist in isolation, they actively contribute to the evolution of their galactic neighborhoods. One of their most significant roles lies in star cluster dynamics. Quadruple systems, with their complex gravitational interactions, can influence the motions of other stars within their clusters, creating ripples that affect the cluster's overall structure and stability. Over time, these interactions can lead to the dispersal or reorganization of stars, altering the cluster's density and even triggering the formation of new stellar groupings. Beyond star clusters, quadruple systems also impact the distribution of matter across galaxies. Their powerful gravitational fields can pull in and redistribute gas and dust, influencing where and how new stars form. In some cases, the gravitational tug-of-war between the stars in a quadruple system can eject material into the surrounding space, seeding regions with the raw ingredients for future star birth. This process not only enriches the galaxy's interstellar medium, but also shapes the overall architecture of the galaxy over millions of years. Interestingly, quadruple systems can also serve as cosmic anchors, helping to stabilize regions of a galaxy that might otherwise be prone to chaotic motion. By anchoring nearby stars and material, these systems can create pockets of relative calm in an otherwise turbulent galactic environment. This stability can encourage the formation of planetary systems and other structures, further contributing to the galaxy's evolution. As we study these systems, we begin to see how even the smallest components of the universe, like a quartet of stars, can have a profound impact on the largest scales. Quadruple star systems are not just fascinating in their own right, they are essential players in the grand story of galactic evolution, weaving their influence into the very fabric of the cosmos. Now, let's shift our focus to a discovery that uncovers the hidden details of quadruple star systems through the lens of their light. Some of these systems exhibit unusual spectral signatures, which are like cosmic fingerprints revealing the secrets of their composition and environment. These signatures, captured through spectroscopy, tell us about the elements present in the stars, their temperatures, and even the conditions in the space surrounding them. In certain quadruple systems, astronomers have observed spectral lines that don't match the expected patterns of normal stars. For example, some systems show unusually high levels of heavy elements like iron or carbon, hinting at past interactions or collisions that enriched their atmospheres. Others display broad or distorted spectral lines, suggesting intense magnetic fields or rapid rotation that stretches the light emitted by the stars. These anomalies provide clues about the stars' histories and the complex processes at work within their systems. Another fascinating aspect is how these spectral signatures can reveal the presence of gas and dust in the system's environment. In some cases, the light from the stars is absorbed or scattered by surrounding material, creating dips or spikes in the spectrum. This tells us that the system is embedded in a cloud of interstellar matter, which could be the remnants of past star formation or the building blocks for future planets. What's truly remarkable is how these unusual signatures challenge our assumptions about stellar behavior. They force us to reconsider how stars evolve in multi-star systems and how their interactions shape their chemical makeup. By studying these spectral puzzles, astronomers gain a deeper understanding of the diversity and complexity of quadruple star systems, opening new doors to exploring the mysteries of the universe. As we continue to decode these cosmic fingerprints, we uncover not just the stories of individual stars, but also the broader narrative of how stellar systems interact and evolve over time. These spectral signatures are more than just scientific curiosities. They are windows into the hidden processes that shape the cosmos. Up next, we'll explore how the presence of 4 stars impacts the habitability of planets orbiting them, a discovery that could redefine our search for life beyond Earth. Now, let's turn our attention to one of the most intriguing questions in astronomy. Could life exist in the chaotic environments of quadruple star systems? The presence of 4 stars introduces a host of challenges for any planets orbiting them, but it also opens up fascinating possibilities. Imagine a planet bathed in the light of multiple suns, with complex gravitational forces shaping its orbit and climate. For astronomers, these systems are both a puzzle and a potential goldmine for understanding how life might arise in extreme conditions. One of the biggest challenges for planets in quadruple systems is the stability of their orbits. With four stars pulling and pushing on each other, a planet's path can be highly unpredictable. Some planets might be flung out of the system entirely, while others could end up in wildly elliptical orbits that cause extreme temperature swings. These conditions make it difficult for life to establish a foothold, as the planet's surface could alternate between scorching heat and freezing cold. Yet, there's also the possibility of life finding a way to thrive. Take, for example, a planet in a stable orbit far enough from the chaotic inner regions of the system. Such a planet could receive steady light and warmth from multiple stars, creating a unique environment with extended daylight hours or even multiple sunsets. The presence of four stars could also lead to a more diverse energy supply, with plants potentially evolving to harness light from multiple sources. Another intriguing factor is how the gravitational interactions between the stars might influence the planet's climate. Tidal forces could heat the planet's interior, leading to volcanic activity that releases gases into the atmosphere. Over time, this might create a stable atmosphere capable of supporting life. Additionally, the complex dynamics of quadruple systems could lead to the formation of protective magnetic fields, shielding the planet from harmful radiation and creating a safer environment for life to emerge. Of course, the search for habitable planets in quadruple systems is still in its early stages. Astronomers are using advanced telescopes and simulations to study these systems, looking for signs of stable orbits and conditions that could support life. While the challenges are significant, the potential rewards are immense. Discovering a habitable planet in a quadruple star system would not only expand our understanding of where life could exist, but also challenge our assumptions about the resilience and adaptability of living organisms. As we continue to explore these complex systems, we're reminded that the universe is full of surprises. Quadruple star systems, with their chaotic orbits and intense gravitational forces, might seem unlikely places for life, but they also offer a glimpse into the incredible diversity of environments that exist beyond our solar system. Up next, we'll dive into the role of tidal interactions in quadruple star systems, uncovering how these forces shape the stars and planets within them. Shifting our focus to the powerful forces at play within quadruple star systems, let's explore the fascinating role of tidal interactions. Tidal forces, familiar from our own moon's influence on Earth's oceans, take on a whole new level of complexity when four stars are involved. In these systems, the gravitational pull between stars doesn't just affect their orbits, it can also dramatically alter their shapes and even their internal processes. When stars in a quadruple system pass close to one another, tidal forces stretch and compress them, much like the way a rubber ball might deform under pressure. This distortion isn't just a one-time event. It happens continuously as the stars orbit each other, leading to a constant tug of war that heats them up. This tidal heating can cause stars to glow brighter or even trigger unusual activity on their surfaces, such as flares or increased radiation, but the effects don't stop there. Tidal forces can also influence the orbits of the stars themselves, nudging them into more circular paths over time or, in some cases, creating even more chaotic trajectories. For stars locked in tight orbits, these forces can lead to a phenomenon called tidal locking, where one star always faces the same side toward its companion, much like how our moon always shows the same face to Earth. This locking effect can further alter the star's rotation and internal dynamics, sometimes leading to unexpected behaviors like magnetic field enhancements or changes in stellar winds. The impact of tidal forces extends to any planets orbiting these stars as well. Planets caught in the gravitational crossfire of multiple stars can experience intense tidal heating of their own, potentially leading to volcanic activity or even the creation of subsurface oceans. These conditions, while extreme, could provide the energy and resources needed for life to emerge, even in such a chaotic environment. Understanding tidal interactions in quadruple systems is crucial for unraveling their evolution and stability. These forces can either bring stars closer together, leading to potential mergers, or push them apart, altering the system's structure over time. By studying these interactions, astronomers gain insights into how multiple star systems form, evolve, and eventually meet their fate. As we delve deeper into the complexities of quadruple systems, it's clear that tidal forces play a pivotal role in shaping their dynamics. From heating stars to influencing orbits, these interactions are a key piece of the puzzle in understanding the universe's most intricate stellar arrangements. Coming up next, we'll examine the largest known quadruple star system, a cosmic giant that pushes the boundaries of what we thought was possible. Now, let's turn our attention to a true cosmic giant, the largest known quadruple star system. This colossal arrangement of 4 stars stretches across an immense region of space, dwarfing many of the other systems we've explored. Its sheer size and scale make it a fascinating subject for astronomers, but they also present unique challenges when it comes to observation and study. To put it into perspective, this system spans a distance so vast that it takes light, traveling at an incredible speed of 300,000 kilometers per second, a significant amount of time to cross from one end to the other. The stars within this system are not only massive in size but also separated by enormous distances, which adds another layer of complexity to their gravitational interactions. One of the biggest challenges in studying this system is its scale. With stars so far apart, their gravitational influence on each other is weaker compared to tighter quadruple systems. This makes their orbits less predictable and harder to model, requiring advanced computational tools and precise observations. Additionally, the immense distances mean that any changes in their positions or movements take much longer to observe, requiring patience and long-term monitoring. Despite these challenges, studying the largest known quadruple system provides valuable insights into the diversity of stellar arrangements in the universe. It challenges our understanding of how such systems form and evolve, especially when the stars involved are not only massive but also widely separated. Astronomers are particularly interested in how these stars manage to remain gravitationally bound over such vast distances and what processes might have led to their current configuration. This system also offers a unique opportunity to study the effects of isolation. Unlike many quadruple systems where the stars are relatively close and interact frequently, the stars in this colossal system are isolated from one another for long periods. This isolation can lead to different evolutionary paths for each star, offering a glimpse into how stellar properties can diverge even within the same system. As we continue to explore the mysteries of quadruple star systems, the largest known example stands as a testament to the incredible variety and scale of the universe. Its unique characteristics remind us that there is still so much to learn about these cosmic arrangements and the forces that shape them. Next, we'll delve into systems where the stars' orbits are highly asymmetric, adding yet another layer of complexity to our understanding of quadruple systems. Shifting our gaze to another intriguing phenomenon, let's explore quadruple star systems where the stars' orbits are anything but ordinary. These systems feature highly asymmetric or irregular orbits, creating a cosmic dance that defies the neat, predictable patterns we often associate with stellar systems. The irregularity of these orbits offers a fascinating glimpse into the chaotic forces at play in the universe and provides crucial clues about how such systems came to be. In these asymmetric systems, the stars follow paths that are uneven, elongated, or tilted relative to one another. Unlike the more circular and aligned orbits seen in some quadruple systems, these irregular paths suggest a turbulent past. One of the leading theories is that these systems may have formed through dynamic interactions, such as close encounters or collisions with other stars or stellar clusters. These violent events could have disrupted the initial orbits, leaving behind the chaotic patterns we observe today. The irregularity of these orbits also has significant implications for the stars' gravitational interactions. In systems with symmetric orbits, the gravitational forces tend to balance out over time, leading to more stable configurations. However, in asymmetric systems, the uneven distribution of mass and the varying distances between stars create constant gravitational tug-of-war. This ongoing instability can lead to dramatic changes in the star's orbits, making these systems some of the most dynamic and unpredictable in the universe. Studying these systems helps astronomers piece together their histories. For instance, the degree of asymmetry in the orbits can reveal how long ago the disruptive event occurred and how much the system has evolved since then. In some cases, these irregularities may even hint at the presence of unseen objects, such as rogue planets or black holes, whose gravitational influence could have caused the orbits to become distorted. One particularly striking example of an asymmetric quadruple system is HD 9880, a system where the star's orbits are so irregular that they appear almost random at first glance. Yet, upon closer examination, astronomers have been able to trace these orbits back to a series of close encounters that occurred millions of years ago. This discovery not only sheds light on the system's past, but also underscores the complexity of stellar dynamics in multiple star systems. As we continue to uncover the secrets of asymmetric quadruple systems, we gain a deeper appreciation for the chaotic and ever-changing nature of the cosmos. These systems remind us that the universe is far from static, with stars constantly influencing and reshaping one another in ways that challenge our understanding. Next, we'll turn our attention to the potential for stellar collisions in quadruple systems, where the stakes are even higher and the outcomes even more dramatic. Now, let's dive into the dramatic and high-stakes world of stellar collisions in quadruple star systems. The gravitational chaos inherent in these systems doesn't just lead to irregular orbits, it can also set the stage for stars to collide. These collisions are rare but monumental events capable of reshaping entire systems and producing some of the most exotic objects in the universe. In quadruple systems, the close proximity of four stars, combined with their complex gravitational interactions, increases the likelihood of such collisions. Unlike binary systems where two stars orbit each other in a relatively stable fashion, quadruple systems are far more dynamic. The constant gravitational tug-of-war between the stars can destabilize their paths, bringing them dangerously close to one another. Over time, this instability can culminate in a catastrophic collision. When two stars collide, the result is nothing short of spectacular. Depending on their masses and the angle of impact, the collision can lead to the formation of a new, more massive star. In some cases, the combined mass of the colliding stars can trigger the birth of a blue straggler, a star that appears younger and brighter than its neighbors due to the infusion of fresh material. These blue stragglers are often observed in star clusters and are thought to form through similar processes. But collisions in quadruple systems can also produce more exotic outcomes. For instance, if one of the colliding stars is a white dwarf, the collision could trigger a supernova, releasing an immense amount of energy and leaving behind a neutron star or even a black hole. Such events not only transform the system but also contribute to the enrichment of the surrounding space with heavy elements, which are essential for the formation of planets and potentially life. The study of these collisions provides valuable insights into the life cycles of stars and the evolution of multiple star systems. By observing the remnants of past collisions, astronomers can piece together the sequence of events that led to these dramatic encounters. For example, the presence of unusual stellar objects or unexpected orbital patterns can serve as clues to the system's violent history. One intriguing case is the quadruple system KIC 28-5506, where astronomers suspect a past collision may have led to the formation of a highly unusual star with an inflated envelope. This star's unique properties suggest it underwent a dramatic merger, reshaping the system's dynamics and leaving behind a stellar remnant that continues to puzzle scientists. As we explore the potential for stellar collisions in quadruple systems, we're reminded of the immense power and unpredictability of the cosmos. These collisions are not just destructive events, they are also creative forces, capable of giving birth to new stars and exotic objects that push the boundaries of our understanding. Next, we'll examine quadruple systems where the stars' orbits are unstable, exploring how this instability shapes their future and the broader implications for stellar evolution. Shifting our focus to the unpredictability of stellar orbits, let's explore quadruple systems where the stars' paths are anything but stable. In these systems, the delicate balance of gravity is often disrupted, leading to orbits that are chaotic and prone to dramatic changes over time. Unlike simpler systems where stars follow predictable paths, the interplay of four stars creates a gravitational dance that can spiral into instability. The instability in these orbits arises from the complex interactions between the stars. Each star exerts a gravitational pull on the others, and in quadruple systems, these forces are constantly shifting. Even a slight nudge from one star can alter the trajectory of another, setting off a chain reaction that destabilizes the entire system. Over thousands or even millions of years, these shifts can lead to wildly different orbital configurations, making it nearly impossible to predict how the system will evolve. One of the most fascinating aspects of these unstable systems is their potential for dramatic transformations. For instance, a star that starts in a distant orbit might gradually move closer to the others, increasing the risk of collisions or ejections. In some cases, a star could be flung out of the system entirely, leaving behind a trio of stars to navigate their new, altered dynamics. These changes can significantly impact the system's longevity, as the loss or addition of a star reshapes the gravitational landscape. The instability also has profound implications for the stars themselves. Stars in unstable orbits are often subjected to extreme gravitational stresses, which can heat them up, distort their shapes, or even trigger internal changes. For example, a star that is repeatedly tugged by its companions might experience heightened stellar activity, such as increased flares or mass ejections. This, in turn, can affect the surrounding environment, influencing the formation of planets or the behavior of other stars in the system. Astronomers study these unstable systems to better understand the limits of gravitational dynamics. By observing how orbits change over time, they can refine models of stellar interactions and predict how other complex systems might behave. One notable example is the system HD 98800, where observations have revealed significant orbital shifts over a relatively short period. These changes provide valuable data for understanding the long-term evolution of quadruple systems and the forces that drive their instability. As we delve deeper into the mysteries of unstable orbits, we're reminded of the ever-changing nature of the cosmos. These systems challenge our understanding of stability and force us to reconsider how stars interact in the vastness of space. Next, we'll turn our attention to quadruple systems where the stars are unusually cold, exploring what makes these stellar objects unique and how they fit into the broader tapestry of the universe. Moving from the chaotic and unstable orbits of quadruple star systems, we now encounter a system that stands out for an entirely different reason. This leads us to the coldest known quadruple star system, a place where the stars defy the typical expectations of stellar behavior. Unlike the blazing temperatures we often associate with stars, these stellar bodies are unusually cold, presenting a fascinating anomaly in the cosmic landscape. In this system, the stars are classified as brown dwarfs, objects that occupy the intriguing space between planets and stars. Brown dwarfs are often referred to as failed stars because they lack the mass needed to sustain the nuclear fusion that powers true stars. As a result, they are significantly cooler, with surface temperatures that can be as low as a few hundred degrees, compared to the thousands or even tens of thousands of degrees found in main sequence stars. What makes this quadruple system particularly unique is the combination of 4 such brown dwarfs orbiting one another. While individual brown dwarfs are rare enough, a system of 4 is an extraordinary find. Their cold temperatures mean they emit most of their light in the infrared spectrum, making them difficult to detect without specialized instruments. This also means they have a much dimmer appearance compared to hotter stars, blending into the cosmic background rather than standing out like traditional stellar objects. The dynamics of this cold quadruple system are equally intriguing. Despite their low temperatures, the gravitational interactions between the brown dwarfs are just as complex as in hotter systems. Their orbits are shaped by the same forces that govern other quadruple systems, but the cooler temperatures add an extra layer of complexity. For instance, the lack of intense heat means that any surrounding material, such as dust or gas, behaves differently than it would around hotter stars. This can influence the formation of planets or other objects in the system, though the process is much slower and less energetic. Astronomers are particularly interested in these cold stars because they provide a glimpse into the lower limits of stellar formation. By studying them, researchers can better understand how objects transition from planets to stars and the conditions necessary for nuclear fusion to ignite. Additionally, the discovery of a quadruple system composed entirely of brown dwarfs challenges existing theories about how such systems form. It raises questions about whether these stars were born together or if they gradually drifted into their current configuration over time. Another fascinating aspect of this system is its potential to host planets. While brown dwarfs are cooler and less luminous than other stars, they can still have orbiting planets, though the conditions would be vastly different from those in systems with hotter stars. Any planets in this system would likely be cold and dim, with surfaces shaped by the unique environment of their parent stars. This opens up new possibilities for the search for exoplanets, particularly in systems that lie outside the traditional definition of habitability. As we explore this coldest known quadruple system, it's clear that these stars offer a unique window into the diversity of the universe. They challenge our assumptions about what stars can be and remind us that the cosmos is full of surprises. Next, we'll take a closer look at quadruple systems where magnetic anomalies add another layer of complexity to these already fascinating stellar arrangements. Now, let's turn our attention to another extraordinary feature of quadruple star systems: magnetic anomalies. These systems, where stars exhibit unusually strong or peculiar magnetic fields, add yet another layer of complexity to these already fascinating stellar arrangements. Magnetic fields in stars are not uncommon, but in quadruple systems, their interactions can create some truly unique and dramatic effects. Magnetic fields in stars are typically generated by the movement of charged particles within their interiors, a process known as dynamo action. In single stars, these fields are often stable and predictable, but in quadruple systems, the presence of multiple stars introduces new dynamics. The gravitational pull between the stars can distort their interiors, altering the flow of charged particles and, in turn, amplifying or modifying their magnetic fields. This can lead to fields that are far stronger or more irregular than those found in isolated stars. One of the most striking consequences of these magnetic anomalies is their impact on stellar activity. Stars with strong magnetic fields often display increased levels of stellar flares, sunspots, and coronal mass ejections. In quadruple systems, these phenomena can be even more pronounced as the magnetic fields of one star can interact with those of its companions. This can lead to a cascade of magnetic events, creating a turbulent environment that can affect the entire system. These magnetic interactions also influence the surrounding space. The magnetic fields can shape the flow of stellar winds, streams of charged particles ejected from the stars. In some cases, these winds can collide, creating shock waves that heat the surrounding gas and dust. This process can lead to the formation of intricate structures, such as magnetic loops or arcs, that are visible in certain wavelengths of light. Astronomers are particularly interested in these systems because they provide a natural laboratory for studying magnetic phenomena. By observing how magnetic fields behave in quadruple systems, researchers can gain insights into the fundamental processes that generate and shape these fields. This knowledge is not only important for understanding stars, but also has broader implications for our understanding of magnetic fields in other cosmic objects, such as planets and galaxies. In addition to their scientific significance, quadruple systems with magnetic anomalies are also visually stunning. The interactions between the stars' magnetic fields can produce spectacular displays of light and energy, making them a favorite subject for both astronomers and astrophotographers. As we continue to explore the mysteries of quadruple star systems, the role of magnetic anomalies stands out as a key area of interest. Next, we'll investigate how these systems contribute to some of the most energetic events in the universe, gamma-ray bursts. Shifting our focus to the most explosive phenomena in the cosmos, we now explore how quadruple star systems play a role in gamma-ray bursts. These bursts are among the most energetic events ever observed, releasing staggering amounts of energy in mere seconds. While gamma-ray bursts are often associated with the collapse of massive stars or the merging of neutron stars, quadruple systems add another layer of complexity to this cosmic puzzle. In these systems, the gravitational interactions between four stars can create conditions ripe for extreme events. When two stars in a quadruple system collide or merge, the resulting explosion can produce a gamma-ray burst. The presence of additional stars nearby can further amplify the event, as their gravitational forces influence the dynamics of the collision. This makes quadruple systems a unique breeding ground for some of the most powerful bursts in the universe. Another intriguing scenario involves black holes, which can sometimes form in quadruple systems. If one of the stars collapses into a black hole, it can begin to consume its companions. The intense gravitational forces at play can lead to the formation of a relativistic jet, a narrow beam of particles traveling at nearly the speed of light. When such a jet is pointed toward Earth, we observe it as a gamma-ray burst. The chaotic environment of a quadruple system increases the likelihood of these jets being produced, making these systems key players in the study of gamma-ray bursts. The aftermath of these events is equally fascinating. The energy released by a gamma-ray burst can outshine entire galaxies for a brief moment, leaving behind a glowing remnant known as an afterglow. In quadruple systems, this afterglow can be observed interacting with the remaining stars and their magnetic fields, providing astronomers with valuable insights into the physics of these events. Understanding the role of quadruple systems in gamma-ray bursts not only sheds light on the mechanisms behind these cosmic fireworks, but also helps us piece together the broader picture of stellar evolution and the life cycles of stars. As we continue to study these systems, they reveal themselves to be not just collections of stars but dynamic laboratories for some of the universe's most extraordinary phenomena. With this in mind, our journey through the mysteries of quadruple star systems continues as we uncover another fascinating aspect: the presence of flare stars and their dramatic outbursts of energy. Now, let's turn our attention to a phenomenon that adds a flash of drama to the cosmic stage: flare stars in quadruple systems. These stars are known for their sudden and intense outbursts of energy, which can brighten them dramatically in a matter of seconds. In quadruple star systems, the presence of flare stars introduces an additional layer of unpredictability and excitement. Flare stars, also known as red dwarfs, are typically small and relatively cool compared to other stars. However, their magnetic activity is anything but calm. When their magnetic fields become twisted and tangled, they release massive amounts of energy in the form of flares. These flares can be hundreds or even thousands of times more powerful than solar flares emitted by our own sun. In a quadruple system, the gravitational interactions between the four stars can amplify this magnetic activity, making flares even more frequent and intense. The effects of these flares ripple through the entire system. Nearby stars can be bombarded with high-energy radiation, which can strip away their atmospheres or alter their chemical compositions. Planets orbiting these stars, if they exist, face an even greater challenge. The intense radiation from flares can make these worlds inhospitable, destroying any potential for life as we know it. Despite their destructive potential, flare stars in quadruple systems provide astronomers with valuable insights. By studying these flares, scientists can learn more about the behavior of magnetic fields in extreme environments. They also offer clues about the early stages of stellar evolution, as young stars often exhibit similar flare activity. Moreover, the presence of flare stars in quadruple systems highlights the dynamic nature of these stellar groups. The interplay of gravity, magnetism, and radiation creates a constantly shifting environment where even the smallest stars can have a big impact. As we continue to observe these systems, they remind us that the universe is full of surprises, where even the most unassuming stars can steal the show. Next, we delve into the isolation of certain quadruple star systems, exploring how these rare configurations form and thrive in the vastness of space. Moving from the chaotic interactions of flare stars, we now explore the quiet solitude of the most isolated quadruple star system ever discovered. Unlike the bustling gravitational dances we've seen in other systems, this one stands alone, far removed from the influence of neighboring stars or clusters. Its isolation raises intriguing questions about how such a system came to be and what it means for its long-term evolution. This unique quadruple system formed in a region of space where star density is exceptionally low. Typically, multiple star systems arise from the fragmentation of dense molecular clouds, where the close proximity of material encourages the birth of multiple stars. However, in this case, the stars likely formed from a rare, isolated cloud that managed to collapse and fragment on its own, creating four stars bound together by gravity but surrounded by vast emptiness. The isolation of this system has profound implications for its evolution. Without the gravitational tug of nearby stars or the disruptive forces of passing stellar neighbors, the orbits of these four stars remain remarkably stable over long periods. This stability allows astronomers to study the system's dynamics with fewer variables, providing a clearer picture of how quadruple systems evolve in ideal conditions. Moreover, the lack of external influences means that any planets within this system would experience a relatively undisturbed environment. While the stars themselves may still interact gravitationally and magnetically, the absence of nearby stars reduces the risk of catastrophic events like stellar collisions or abrupt changes in orbit. This makes the system a fascinating laboratory for understanding how planets might form and survive in quadruple systems. The discovery of this isolated system also challenges our understanding of star formation. It suggests that even in the emptiest regions of space, the processes that give rise to multiple stars can still occur, albeit less frequently. This opens up new possibilities for where we might find other quadruple systems in the universe, especially in areas previously thought too sparse for such complex formations. As we leave this solitary quartet behind, we turn our attention to systems with retrograde orbits, where stars move in opposing directions, adding another layer of complexity to the cosmic dance. Shifting our gaze to a new cosmic phenomenon, we now delve into the intriguing world of quadruple star systems with retrograde orbits. In these systems, one or more stars defy the norm by orbiting in the opposite direction of their companions, creating a celestial dance that is as puzzling as it is mesmerizing. Retrograde orbits, where a star moves in the opposite direction to the rest of its system, are rare but not unheard of. In quadruple systems, this backward motion adds a layer of complexity to the already intricate gravitational interactions. One prevailing theory suggests that retrograde orbits may result from a close encounter with another star or system in the past. During such an encounter, the gravitational pull of the passing star could have disrupted the original orbits, flipping one or more stars into a backward trajectory. Another possibility is that retrograde orbits are a remnant of the system's chaotic formation process. As stars coalesce from a collapsing cloud of gas and dust, interactions between the forming stars can lead to unpredictable orbital configurations. In some cases, this may result in one star being ejected into a retrograde orbit, forever moving against the flow of its siblings. These backward orbits offer a unique window into the history of quadruple systems. By studying the dynamics of retrograde stars, astronomers can piece together clues about the system's past, including whether it experienced violent encounters or underwent a turbulent formation process. The presence of retrograde motion also affects the system's long-term stability, as the opposing orbits can lead to gravitational tugs and pulls that reshape the star's paths over time. One notable example of a quadruple system with retrograde orbits is HD 91962, where two of the four stars move in opposite directions. This system has become a focal point for studying how retrograde motion influences the evolution of multiple star systems. Observations suggest that the backward traveling stars in HD 91962 may eventually destabilize the system, potentially leading to the ejection of one or more stars in the distant future. The study of retrograde orbits in quadruple systems not only deepens our understanding of stellar dynamics, but also challenges our assumptions about how such systems form and evolve. As we continue to explore these cosmic oddities, we uncover new insights into the forces that shape the universe, reminding us that even the stars can dance to their own rhythm. With this backward glance at retrograde orbits behind us, we now turn our attention to systems where stars recycle material, a process that breathes new life into ancient stellar companions. Turning our attention to a cosmic recycling process, we now explore how quadruple star systems can breathe new life into their stellar companions. In these systems, the close proximity and complex gravitational interactions between the four stars create unique opportunities for material exchange. This recycling of matter can lead to the formation of new stars or even rejuvenate aging ones, offering a fascinating glimpse into the dynamic life cycles of multiple star systems. In quadruple systems, the gravitational pull of one star can strip material from another, especially when one star evolves into a red giant and expands. This stolen material, often rich in hydrogen, can accumulate around the receiving star, either reigniting its fusion processes or creating a new protostar in its orbit. This process is particularly common in systems where two stars form a tight binary pair, with their close orbits making it easier for material to transfer between them. One striking example of stellar recycling occurs in systems where a white dwarf, the dense remnant of a dead star, pulls material from a companion star. Over time, this accumulated material can trigger a thermonuclear explosion on the white dwarf's surface, known as a nova. In quadruple systems, the presence of additional stars can complicate this process, leading to more frequent or intense outbursts. These events not only reshape the system but also spread heavy elements into the surrounding space, contributing to the cosmic cycle of star formation. Another fascinating aspect of stellar recycling is the formation of circumbinary disks, where material from one star forms a disk around a binary pair. These disks can eventually collapse to form new stars or planets, adding to the complexity of the system. In quadruple systems, the gravitational influence of four stars can create multiple such disks, leading to a cascade of new stellar and planetary formations. The recycling of material in quadruple systems also has implications for the longevity of stars. By transferring material from an aging star to a younger one, these systems can extend the lives of their stellar members, delaying their eventual demise. This process highlights the interconnectedness of stars within a system, and underscores the importance of studying multiple star systems to understand the broader mechanisms of stellar evolution. As we continue to unravel the mysteries of stellar recycling in quadruple systems, we gain valuable insights into how stars interact, evolve, and influence their cosmic surroundings. These systems remind us that even in the vastness of space, stars are not isolated entities but part of a dynamic, interconnected network. With this exploration of stellar recycling complete, we now turn to a different kind of cosmic mystery: systems that include exotic stellar remnants, where the remains of dead stars play a pivotal role in shaping their environment. Now let's delve into the enigmatic world of quadruple systems that host exotic stellar remnants, where the remnants of dead stars create stunning cosmic phenomena. These remnants, such as neutron stars and white dwarfs, are not just leftovers from stellar deaths but active players that shape the dynamics of their entire systems. Their extreme densities and gravitational pull introduce unique challenges and opportunities in understanding how quadruple systems evolve. Neutron stars, the collapsed cores of massive stars that have exploded as supernova, are incredibly dense, packing the mass of a star into a sphere just a few kilometers across. In quadruple systems, a neutron star's intense gravity can warp the orbits of the other stars, creating chaotic and unpredictable patterns. Its powerful magnetic fields can also emit beams of radiation that sweep across the system, influencing the behavior of nearby stars and any surrounding material. White dwarfs, the remnants of stars like our Sun, play a different but equally fascinating role. These dense stellar cores may appear inert, but in quadruple systems, they often interact with their companions in dramatic ways. For instance, a white dwarf can pull material from a nearby star, accumulating it on its surface. Over time, this can lead to explosive events like nova or even more powerful thermonuclear outbursts, which reshape the system and scatter heavy elements into space. The presence of exotic remnants also affects the orbits of the stars in these systems. A neutron star's gravity can cause nearby stars to spiral inward or outward, altering their trajectories over time. Similarly, a white dwarf's interactions with its companions can lead to the formation of accretion disks, which can fuel new star formation or trigger violent stellar events. One particularly intriguing example is a quadruple system where two binary pairs orbit each other, with one binary containing a neutron star. The neutron star's gravitational influence can cause the other stars to orbit in highly elliptical paths, creating a complex and dynamic dance. This interaction can also lead to the emission of gravitational waves, ripples in spacetime that provide astronomers with valuable insights into the system's inner workings. The study of quadruple systems with exotic remnants offers a window into the dramatic and often violent processes that shape the cosmos. These remnants remind us that even in death, stars continue to influence their surroundings, driving the evolution of their systems and contributing to the rich tapestry of the universe. With this exploration of exotic remnants complete, we now turn to another stellar marvel, the youngest known quadruple star system, where the stars are still in the early stages of their cosmic journey. Now, let's shift our gaze to a cosmic cradle, where the youngest known quadruple star system offers a rare glimpse into the birth of stars. This system, still in its infancy, is a fascinating laboratory for understanding how multiple stars form and interact in the early stages of their lives. At an age of just a few million years, these stars are practically newborns on the cosmic timeline, giving us a front-row seat to the processes that shape stellar systems from their very beginnings. This young quadruple system provides valuable insights into star formation in complex environments. Unlike isolated stars, which form from a single collapsing cloud of gas and dust, multiple stars in a quadruple system must navigate a crowded and dynamic birth environment. Here, gravitational interactions between the stars can influence their formation, causing some stars to grow faster while others may be ejected from the system entirely. These chaotic early stages are crucial for determining the final configuration of the system and the properties of its stars. One of the most striking features of this young system is the presence of protoplanetary disks around its stars. These disks, made of gas and dust, are the birthplaces of planets. In a quadruple system, however, the disks face unique challenges. The gravitational pull of neighboring stars can distort or even disrupt these disks, affecting the formation of planets. Despite these obstacles, some planets may still form, offering a tantalizing possibility of worlds orbiting multiple suns. The study of this young quadruple system also sheds light on the role of turbulence and fragmentation in star formation. The original gas cloud from which these stars formed likely experienced intense turbulence, causing it to break into smaller fragments. These fragments then collapsed to form the individual stars of the system. Observations of this process help astronomers refine their models of how multiple star systems emerge from the chaos of their birth environments. As we continue to observe this system, we may also witness the early signs of stellar evolution. The stars still embedded in their birth cloud are likely accreting material and growing in mass. Some may even exhibit powerful stellar winds or jets, which can sculpt the surrounding gas and dust into intricate shapes. These phenomena provide clues about how stars transition from their formative stages to the main sequence, where they will spend the majority of their lives. The youngest known quadruple star system is a treasure trove of information for astronomers, offering a window into the earliest moments of stellar life. By studying this system, we can better understand the complexities of star formation and the forces that shape multiple star systems. This discovery reminds us that the universe is a dynamic and ever-changing place, where even the youngest stars hold the secrets to our cosmic origins. With this glimpse into the birth of a quadruple system, we now turn to another fascinating discovery: systems where the stars have unusually high levels of heavy elements, and what this means for their evolution and potential for planet formation. Moving from the birth of stars to the elements that shape them, we now explore quadruple star systems with unusually high levels of heavy elements, a characteristic known as high metallicity. Unlike systems with fewer heavy elements, these metal-rich environments provide unique conditions that influence the life cycle of stars and the potential for planet formation. High metallicity in stars means they have a higher proportion of elements heavier than hydrogen and helium, such as iron, oxygen, and carbon. These elements play a critical role in the formation and evolution of stars and their planetary systems. In quadruple star systems, this abundance of heavy elements can lead to fascinating outcomes. For example, stars with high metallicity tend to cool more efficiently, which allows them to form more easily from collapsing gas clouds. This process can result in a higher number of stars forming within the same system, contributing to the complexity of quadruple arrangements. The presence of heavy elements also influences the formation of planets. In metal-rich systems, the protoplanetary disks around stars are more likely to contain the raw materials needed to build rocky planets like Earth. This increases the chances of planetary systems forming within quadruple star systems, despite the gravitational challenges posed by multiple stars. However, the dynamics of these systems can also lead to unusual planetary configurations, such as planets with highly elliptical orbits or those orbiting at great distances from their stars. High metallicity also affects the evolution of stars. Metal-rich stars tend to have stronger stellar winds, which can strip away material and alter their life cycles. Over time, these winds can shape the surrounding environment, influencing the orbits of other stars in the system, and potentially leading to the formation of exotic stellar remnants like white dwarfs or neutron stars. Studying these metal-rich quadruple systems offers valuable insights into the diversity of stellar and planetary systems in the universe. By comparing them to systems with lower metallicity, astronomers can better understand how the chemical composition of a star system shapes its development and the potential for life-sustaining planets. As we delve deeper into the mysteries of quadruple star systems, we next turn to another intriguing discovery: the role these systems play in producing gravitational waves, ripples in space-time caused by the motion of massive objects. Now, let's shift our focus to one of the most fascinating phenomena in the cosmos: gravitational waves. Quadruple star systems play a surprising role in producing these ripples in space-time, which are caused by the motion of massive objects. When four stars interact in complex orbits, their gravitational pull can create extreme distortions in space-time, leading to the emission of gravitational waves. In these systems, the gravitational interactions between the stars are incredibly intense. As the stars orbit one another, their movements generate waves that propagate outward at the speed of light, carrying energy away from the system. These waves are often strongest when the stars are in close, rapid orbits or when they collide, creating a burst of gravitational energy detectable across vast distances. One of the most remarkable aspects of quadruple systems is their potential to produce continuous gravitational waves. Unlike single or binary systems, where gravitational waves are typically emitted during specific events like mergers, quadruple systems can generate a steady stream of waves due to their ongoing chaotic interactions. This makes them valuable targets for observatories like the Laser Interferometer Gravitational Wave Observatory, which can detect these subtle ripples and provide insights into the dynamics of these complex systems. The study of gravitational waves from quadruple systems also helps astronomers test the predictions of Einstein's theory of general relativity. By observing how these waves behave in systems with four stars, scientists can refine their understanding of gravity and spacetime, uncovering new details about the universe's most fundamental forces. Looking ahead, the detection of gravitational waves from quadruple star systems could reveal even more about their origins and evolution. These waves carry information about the masses, distances, and motions of the stars, offering a unique way to study systems that are often too distant or complex to observe directly. As we continue to explore the mysteries of quadruple star systems, we next turn to another intriguing discovery: systems that include rare or unusual types of stars, adding yet another layer of complexity to these cosmic arrangements. Shifting our gaze now to the stars themselves, we find that some quadruple systems host truly extraordinary stellar members. These systems aren't just about the number of stars, but the unusual types of stars they contain. Among these are blue stragglers, stars that appear younger and hotter than their neighbors, defying expectations about stellar evolution. These stars are thought to form through collisions or mass transfer between stars in dense systems, which quadruple star systems often provide. Another fascinating type is the hypergiant, some of the largest and most luminous stars in the universe. When a hypergiant is part of a quadruple system, its immense size and energy output can dominate the dynamics of the group. Its powerful stellar winds and radiation can shape the orbits of the other stars and even influence the formation of planets or other celestial bodies in the system. The presence of these unusual stars adds another layer of complexity to quadruple systems. For example, blue stragglers can alter the gravitational balance, leading to unexpected orbital configurations. Hypergiants, with their short lifespans and eventual explosive deaths, can dramatically reshape the system, leaving behind neutron stars or black holes that further complicate the gravitational interactions. Studying these systems provides astronomers with valuable insights into the processes that create such rare stars. It also helps us understand how these stars influence their surroundings, from altering the orbits of their companions to triggering new rounds of star formation. As we continue to explore the diversity of quadruple systems, we move next to another extraordinary discovery: systems that emit an extraordinary amount of energy, pushing the limits of what we thought possible in stellar dynamics. Now, let's turn our attention to one of the most energetic quadruple star systems ever discovered. In a universe filled with remarkable phenomena, This system stands out for its extraordinary energy output, pushing the boundaries of what we thought possible in stellar dynamics. The source of this immense energy lies in the interactions and behaviors of the stars themselves. At the heart of this system, one or more of the stars are often in a highly active state, emitting vast amounts of radiation and stellar winds. These stars may be undergoing intense fusion processes nearing the end of their lifespans, or even interacting gravitationally in ways that generate massive bursts of energy. In some cases, the presence of a hypergiant star or a star in the process of going supernova can amplify the system's energy output to staggering levels. The effects of this energy extend far beyond the stars themselves. The intense radiation and stellar winds can strip away material from nearby stars, disrupt planetary formation, and even trigger waves of new star formation in the surrounding region. The gravitational forces at play in such a system can also lead to chaotic and unpredictable orbital patterns, further complicating the dynamics of the group. Studying these energetic systems provides astronomers with critical insights into the life cycles of stars and the broader processes that shape galaxies. They also challenge our understanding of how multiple star systems evolve and interact over time. As we continue to explore the wonders of quadruple star systems, we'll next uncover another intriguing discovery: systems where the star's orbits create unique patterns that could serve as cosmic clocks, marking time in ways we've only just begun to understand. Now, shifting our gaze to another fascinating aspect of quadruple star systems, let's explore systems where the star's orbits are shaped like stretched ovals, known as highly elliptical orbits. These systems challenge our expectations of how stars move around one another, offering a glimpse into the chaotic and dynamic nature of space. In such systems, the stars don't follow the neat, circular paths we often imagine. Instead, their orbits are elongated, creating dramatic swings in distance as they travel around one another. The formation of these elliptical orbits is often influenced by gravitational interactions within the system. When four stars share a confined space, their gravitational pulls can tug and distort their paths over time, stretching them into these elongated shapes. External factors like a passing star or the gravitational influence of a nearby galaxy can also play a role in shaping these unusual orbits. What's truly remarkable is what these orbits tell us about the system's history and stability. The highly elliptical paths suggest that these systems may have experienced significant disruptions or close encounters in the past. They also imply that the stars' movements are far from predictable, with their distances from one another varying dramatically over time. This unpredictability can lead to fascinating phenomena, such as stars passing unusually close to one another, triggering intense gravitational interactions or even stellar collisions. It's a reminder of how dynamic and ever-changing these systems can be, offering astronomers a unique laboratory to study the effects of gravity on a grand scale. As we continue our journey through the wonders of quadruple star systems, we'll next delve into their role in the formation and evolution of star clusters, shedding light on how these systems shape the larger structures of the universe. Now, turning our attention to the broader cosmic stage, we find that quadruple star systems play a pivotal role in the formation and evolution of star clusters. These dense collections of stars, bound together by gravity, are shaped in part by the unique dynamics of multiple star systems like quadruples. Within these clusters, quadruple systems act as gravitational anchors, influencing the movements and behaviors of surrounding stars. One way quadruple systems shape star clusters is through their gravitational interactions. The complex orbits of four stars create a web of forces that can pull neighboring stars into new trajectories. Over time, these interactions can lead to the redistribution of stars within the cluster, altering its structure and density. In some cases, quadruple systems can even trigger the formation of new stars by compressing gas and dust in their vicinity, setting off a chain reaction of stellar birth. Additionally, quadruple systems contribute to the overall stability of star clusters. Their gravitational influence helps maintain the cluster's cohesion, preventing stars from drifting apart. However, they can also introduce instability in certain scenarios. For example, close encounters between quadruple systems and other stars or binaries can send stars flying out of the cluster, a process known as stellar ejection. These ejected stars can go on to wander the galaxy, leaving behind a more tightly knit cluster. The presence of quadruple systems also provides valuable insights into the history of star clusters. By studying their orbits and interactions, astronomers can piece together the cluster's past, including how it formed and evolved over billions of years. Quadruple systems serve as cosmic time capsules, preserving clues about the conditions that gave rise to these stellar communities. As we move forward in our exploration, we'll next uncover how quadruple star systems influence the behavior of planets, particularly those with rings, and what this reveals about the diversity of planetary systems in the universe. Shifting our gaze to the planets themselves, we now encounter a fascinating feature within quadruple star systems: exoplanets adorned with rings. These ringed worlds, reminiscent of Saturn in our own solar system, offer a glimpse into the intricate processes of planetary formation and evolution in multi-star environments. In quadruple systems, the presence of 4 stars creates a dynamic and often chaotic gravitational environment. Despite these challenges, some planets manage to retain or even develop rings. These rings often form from the debris left over after the planet's creation, or from material pulled in from nearby asteroids or moons. The gravitational tugs from multiple stars can also shape these rings, causing them to become more complex or even fragmented over time. One of the most intriguing aspects of these ringed planets is what their rings reveal about their histories. For example, gaps in the rings can indicate the presence of moons, while variations in ring density can suggest past collisions or disruptions. In some cases, the rings themselves may act as a record of the planet's interactions with its host stars, preserving evidence of gravitational disturbances or changes in the planet's orbit. What makes these systems even more remarkable is the diversity of rings they exhibit. Some planets may have broad, expansive rings like Saturn, while others might have narrow, faint rings barely visible to telescopes. The composition of these rings can also vary widely, from icy particles to rocky debris, each offering clues about the planet's environment and its place within the quadruple star system. As we continue to study these ringed exoplanets, we gain not only a deeper understanding of their origins, but also insights into the broader processes that shape planetary systems. Next, we'll journey to the farthest reaches of the universe to explore the most distant quadruple star system ever observed and what its isolation tells us about the cosmos. Turning our attention to the far reaches of the cosmos, we now encounter the most distant quadruple star system ever observed. This system, located billions of light years away, pushes the boundaries of our understanding and technology, offering a rare glimpse into the universe's ancient past. Studying such a remote system presents immense challenges. The sheer distance means that the light we observe today began its journey when the universe was much younger, requiring astronomers to peer back in time. Additionally, the faintness of these stars makes them incredibly difficult to detect, even with the most advanced telescopes. Observations often rely on indirect methods, such as analyzing the system's gravitational effects on surrounding objects or detecting its unique spectral signatures. What makes this distant quadruple system so significant is what it reveals about the early universe. Its existence suggests that multiple star systems formed relatively quickly after the Big Bang, challenging previous assumptions about the timeline of cosmic evolution. The dynamics of this system also provide clues about the conditions in the early universe, such as the density of matter and the rate of star formation. Moreover, the study of such distant systems helps us understand how galaxies and larger cosmic structures evolved. By comparing these ancient systems to closer, younger quadruple systems, astronomers can trace the changes in stellar dynamics over billions of years. This distant quadruple star system acts as a cosmic time capsule, preserving the history of the universe's formative years. As we continue to explore these distant corners of space, each discovery brings us closer to unraveling the mysteries of the universe's origins. Next, we'll delve into quadruple systems where the stars are arranged into two binary pairs, and how this unique configuration influences their behavior. Shifting our focus to another fascinating configuration, let's explore quadruple star systems where the stars are arranged into two binary pairs. These systems are like cosmic dance partners, with each pair of stars orbiting each other while also moving around a shared center of gravity with the other pair. This unique setup creates a delicate balance of gravitational forces, making these systems both stable and intriguing to study. In such systems, the inner dynamics of each binary pair are relatively predictable, with the stars following well-defined orbits. However, the interaction between the two pairs adds a layer of complexity, as their gravitational pull influences each other's movements. This interplay can lead to fascinating phenomena, such as periodic changes in orbital speeds or slight shifts in the star's positions over time. What makes binary pair quadruple systems stand out is their stability compared to other quadruple configurations. Systems where all four stars orbit in a more chaotic arrangement are prone to gravitational disturbances, but the binary pair structure tends to maintain its form over long periods. This stability allows astronomers to study these systems in greater detail, providing insights into the long-term behavior of multiple star systems. Interestingly, binary pair quadruple systems also offer a glimpse into how stars form and evolve in groups. The pairs often form from the same cloud of gas and dust, and their interactions can influence the system's overall development. For example, material exchange between the pairs can trigger new bursts of star formation or even lead to the creation of planets within the system. As we compare these systems to other quadruple configurations, it becomes clear that their structure plays a crucial role in shaping their dynamics. The binary pair arrangement not only adds stability, but also creates unique opportunities for studying the intricate relationships between stars. Up next, we'll examine how quadruple star systems produce powerful stellar winds and the effects these winds have on their surroundings. Now, let's turn our attention to the role of quadruple star systems in producing powerful stellar winds. These winds are streams of charged particles ejected from the surfaces of stars, and in quadruple systems, they can become particularly intense due to the complex interactions between the stars. When four stars are in close proximity, their combined gravitational forces and radiation can amplify the strength and reach of these winds, creating a dynamic and energetic environment. In such systems, stellar winds are not only influenced by each individual star, but also by the interactions between them. For instance, when two stars in a quadruple system are close together, their winds can collide, producing shock waves that heat the surrounding gas and dust. These collisions can also create regions of high energy where particles are accelerated to incredible speeds. Over time, this process can shape the structure of the entire system, carving out intricate patterns in the surrounding material. The effects of these winds extend far beyond the stars themselves. In quadruple systems, the combined stellar winds can push material outward, creating vast bubbles of hot gas that expand into the surrounding space. These bubbles can influence the formation of new stars or even planets by compressing nearby gas and dust clouds. In some cases, the winds can strip away material from protoplanetary disks, potentially altering the course of planet formation. Interestingly, stellar winds from quadruple systems can also interact with other cosmic phenomena, such as nearby nebulae or interstellar clouds. When these winds collide with external material, they can trigger shock waves that lead to the formation of bright, glowing regions known as bow shocks. These structures are not only visually stunning, but also provide valuable insights into the dynamics of stellar winds and their impact on the interstellar medium. As we continue to study quadruple star systems, the role of stellar winds remains a key area of interest. These winds not only shape the systems themselves, but also influence their broader environment, highlighting the interconnected nature of stellar evolution. Next up, we'll delve into quadruple systems with unusual dust clouds and the mysteries they hold. Now, let's shift our focus to quadruple star systems with unusual dust clouds. These clouds, often swirling around the stars in intricate patterns, add another layer of complexity to these already fascinating systems. Dust clouds in quadruple systems are not just random collections of particles. They are shaped by the unique dynamics of four stars interacting with one another. The gravitational pull and radiation from each star can sculpt these clouds into stunning formations, creating a cosmic ballet of dust and light. The origins of these dust clouds can vary widely. In some cases, they are remnants of the material from which the stars themselves formed. As the stars evolved, they expelled gas and dust, which then settled into clouds around the system. In other cases, the dust clouds may have formed later, as the stars interacted with each other or with external material, such as passing interstellar clouds. The presence of multiple stars means that these dust clouds are constantly being reshaped, creating a dynamic and ever-changing environment. These dust clouds play a crucial role in the evolution of quadruple star systems. They can act as a reservoir of material, feeding the stars and influencing their growth. At the same time, the dust can absorb and scatter light, altering the way we observe these systems from Earth. In some cases, the dust clouds can even trigger the formation of new stars or planets as they collapse under their own gravity. One of the most intriguing aspects of these dust clouds is how they interact with the star's radiation. The intense light and heat from four stars can heat the dust to high temperatures, causing it to glow in infrared light. This makes these systems particularly fascinating for astronomers studying the invisible wavelengths of the universe. The dust clouds can also reveal clues about the stars' ages, compositions, and histories, providing a window into the past of these complex systems. As we continue to explore quadruple star systems, the study of these unusual dust clouds offers a unique perspective on the processes that shape stellar environments. Next, we'll uncover the mysteries of the most compact quadruple system known, where stars are packed together in an extraordinary way. Turning our attention to an even more extraordinary phenomenon, we now explore the most compact quadruple star system ever discovered. Imagine four stars orbiting each other in a space so confined that their gravitational interactions become intensely chaotic and unpredictable. This system, where the stars are packed unusually close together, pushes the boundaries of what we thought possible in stellar dynamics. The proximity of these stars creates a gravitational environment unlike anything seen in more widely spaced systems. The stars' orbits are tightly intertwined, leading to frequent close encounters that can dramatically alter their paths. These interactions generate immense tidal forces, which can distort the stars' shapes and even trigger eruptions of material from their surfaces. For astronomers, studying this system is both a challenge and an opportunity. The sheer density of stars in such a small area makes it difficult to observe individual components clearly, but it also offers a unique laboratory for understanding how stars behave under extreme conditions. This compact system also provides valuable insights into the processes of star formation. The fact that four stars can form and remain stable in such a confined space suggests that the initial conditions of their birth cloud were exceptionally dense. It raises questions about how these stars avoid colliding with one another or merging into a single, more massive star. The dynamics of this system could shed light on the mechanisms that allow multiple stars to coexist in close quarters, a phenomenon that might be more common in the universe than we previously thought. Moreover, the intense gravitational interactions in this system can accelerate processes like stellar evolution. The stars here may age faster than those in less crowded environments due to the constant gravitational stress they experience. This could lead to the formation of exotic stellar objects such as black holes or neutron stars much earlier than expected. As we continue to study this remarkable system, it challenges our understanding of stellar mechanics and opens new avenues for research. Next, we'll delve into quadruple systems with multiple protostars, where the process of star formation is still unfolding, offering a glimpse into the birth of these celestial wonders. Shifting our focus to the cosmos' youngest inhabitants, we now explore quadruple systems with multiple protostars. These systems offer a rare glimpse into the very beginning of stellar life, where stars are still in the process of forming. Unlike fully developed systems, these stellar nurseries are filled with swirling clouds of gas and dust, gradually collapsing to give birth to new stars. In these systems, the protostars are often surrounded by thick, dense envelopes of material that obscure their light, making them challenging to observe. Yet, through advanced imaging techniques, astronomers have been able to peer into these cosmic cradles. What they've found is a chaotic yet fascinating environment, where the gravitational pull of each protostar battles for dominance, shaping the surrounding material into intricate patterns. One of the most striking features of these systems is the presence of accretion disks. These disks of gas and dust orbit the protostars, funneling material onto their surfaces and fueling their growth. In quadruple systems, the interactions between these disks can be incredibly complex, sometimes leading to the creation of spiral arms or even the ejection of material into space. These processes play a crucial role in determining the final masses and orbits of the stars. Moreover, the study of these systems sheds light on the early stages of star formation itself. By examining how multiple protostars form and interact within a single system, astronomers can better understand the conditions that lead to the birth of stars. It also raises intriguing questions about how these stars avoid merging into a single massive object and how their orbits evolve over time. These systems also provide clues about the origins of planets. The same disks that feed the protostars can later become the birthplaces of planets, offering a window into how planetary systems form in the presence of multiple stars. As we continue to unravel the mysteries of these young quadruple systems, we gain not only a deeper understanding of star formation, but also a clearer picture of the dynamic processes that shape the universe. Next, we'll explore the role of quadruple systems in stellar feedback, where their influence extends far beyond their immediate surroundings, shaping the very fabric of space. Turning our gaze to the broader impact of quadruple star systems, we now delve into their role in stellar feedback. These systems are not just isolated cosmic phenomena. They actively shape their surroundings through powerful forces like radiation, stellar winds, and supernova. This feedback process plays a critical role in influencing the dynamics of the regions around them, often triggering new waves of star formation or even halting it altogether. In quadruple systems, the combined output of 4 stars can produce an extraordinary amount of radiation. This intense energy heats up the surrounding gas and dust, causing it to expand and disperse. Such interactions can create vast bubbles of hot gas which sweep through the interstellar medium, clearing out material and carving out new structures. These bubbles can compress nearby gas clouds, sometimes leading to the birth of new stars in a ripple effect that extends far beyond the system itself. Stellar winds, another key component of stellar feedback, are particularly intense in quadruple systems. Each star ejects streams of charged particles into space, and when 4 stars are involved, these winds can collide and create shock waves. These shock waves heat up the surrounding material, producing X-rays and other forms of high-energy radiation that astronomers can observe. The interplay of these winds can also strip away material from nearby protoplanetary disks, affecting the formation of planets in the vicinity. Perhaps the most dramatic form of stellar feedback comes from supernova. When a massive star in a quadruple system reaches the end of its life and explodes, it releases an immense amount of energy and heavy elements into space. This explosion can trigger the collapse of nearby gas clouds, seeding the next generation of stars and planets. In quadruple systems, the presence of multiple stars can complicate this process, as the explosion's effects are shaped by the gravitational interactions within the system. Understanding stellar feedback in quadruple systems helps astronomers piece together the complex puzzle of how galaxies evolve. These systems, with their combined forces, act as cosmic sculptors, shaping the distribution of matter and energy in their surroundings. By studying them, we gain insights into how the universe recycles material and drives the cycle of star birth and death. Looking ahead, we'll explore quadruple star systems with exotic planetary systems, where planets orbit under the influence of 4 stars, creating some of the most unusual and fascinating worlds in the cosmos. Now, let's shift our focus to one of the most intriguing aspects of quadruple star systems, the exotic planetary systems that orbit them. Imagine a world where not 1, but 4 suns light up the sky, creating a cosmic ballet of gravity and light. These planets, often with extreme orbits or multiple moons, offer a glimpse into the incredible diversity of planetary systems in the universe. In such systems, the gravitational dance of 4 stars creates chaotic and dynamic environments. Planets here often follow highly irregular paths, sometimes looping around one pair of stars before being tugged by another. These extreme orbits challenge our understanding of planetary stability and raise fascinating questions about how planets can survive in such conditions. Some of these worlds even have multiple moons, adding another layer of complexity to their already intricate systems. One remarkable example is a planet orbiting a quadruple system with an orbit so elongated that it spends part of its year close to the stars and part of it far out in the frozen reaches of space. This extreme variation in temperature and light creates a world of stark contrasts where conditions change dramatically over time. Such planets push the boundaries of what we consider habitable and force us to rethink the possibilities for life in the cosmos. The presence of multiple moons in these systems adds yet another layer of wonder. In some cases, moons orbit planets in quadruple star systems, creating a cascade of gravitational interactions that can lead to tidal heating, volcanic activity, or even the formation of subsurface oceans. These moons, much like the moons in our solar system, could hold the key to understanding the potential for life beyond Earth. What do these exotic planetary systems tell us about the diversity of the cosmos? They reveal that the universe is far more inventive than we ever imagined. Planets in quadruple systems defy our expectations, showing us that planetary formation can occur in even the most extreme environments. By studying these worlds, we gain insights into the resilience and adaptability of planetary systems, broadening our search for life and deepening our understanding of the universe's complexity. Next, we'll explore the most massive quadruple star system ever discovered, where the sheer scale and power of these cosmic giants challenge our understanding of stellar formation and dynamics. Moving on from the exotic planetary systems, let's turn our attention to the most massive quadruple star system ever discovered. This colossal system, a true giant among giants, defies our expectations and pushes the boundaries of what we know about stellar formation. With stars so massive and packed with energy, it's a cosmic marvel that challenges our understanding of how these systems come to be. Studying such a massive system is no small feat. The sheer size and intensity of the stars create significant challenges for astronomers. The gravitational forces at play are immense, making it difficult to predict the orbits and interactions of the stars. Observing this system requires advanced technology and innovative methods to capture the dynamic processes unfolding within it. What makes this system truly fascinating is what it reveals about the limits of stellar formation. These stars are among the largest and most energetic ever observed, pushing the boundaries of how big and powerful stars can become. Their existence raises questions about the conditions needed for such massive stars to form and whether there is an upper limit to their size. The most massive Quadruple system also provides valuable insights into the life cycles of stars. The intense radiation and stellar winds from these giants shape their surroundings, influencing the formation of new stars and planets. By studying this system, astronomers can better understand the role of massive stars in the evolution of galaxies and the universe as a whole. As we continue to explore the mysteries of quadruple star systems, this massive system stands as a testament to the incredible diversity and scale of the cosmos. It challenges our assumptions and expands our knowledge, reminding us that the universe is full of surprises waiting to be uncovered. Next, we'll dive into quadruple star systems with unusual timekeeping, where the star's orbits create unique patterns that could serve as cosmic clocks. Now, let's shift our focus to an entirely different kind of mystery in quadruple star systems: their ability to act as cosmic clocks. Imagine a celestial dance so precise and rhythmic that it could help us measure time on a cosmic scale. These systems, with their intricate and predictable orbital patterns, offer a fascinating glimpse into how the universe keeps its own time. In some quadruple systems, the stars move in such a way that their orbits create repeating and highly regular patterns. These patterns are so consistent that astronomers can use them to track the passage of time over vast periods. It's like having a giant clock in the sky, ticking away with the precision of nature's most finely tuned mechanisms. The implications of this are profound. By studying these systems, we gain new insights into the nature of time itself. Time, as we experience it on Earth, is a human construct, but in the vastness of space, it's marked by the movements of stars and galaxies. These quadruple systems act as natural timekeepers, helping us understand how time flows on a universal scale. But it's not just about measuring time. These systems also challenge our understanding of space and motion. The way the stars move in such predictable orbits reveals the underlying laws of gravity and dynamics that govern the cosmos. It's a reminder that even in the most chaotic environments, there's an underlying order waiting to be discovered. Furthermore, these cosmic clocks could have practical applications. For instance, they might serve as reference points for future space navigation, or even help us calibrate astronomical instruments with greater precision. The more we study these systems, the more we realize their potential to unlock new frontiers in space exploration. As we wrap up this discovery, let's move on to the role of quadruple star systems in galactic collisions, where these complex systems continue to defy expectations and reveal the universe's endless capacity for wonder. Turning our gaze to the vast and violent events shaping the cosmos, let's delve into the role quadruple star systems play during galactic collisions. These collisions, where entire galaxies smash into one another, are some of the most dramatic events in the universe. Yet, amidst this chaos, quadruple star systems often not only survive but thrive, offering a unique window into these cataclysmic encounters. When galaxies collide, the gravitational forces at play are immense, tearing apart stars, planets, and even black holes. But quadruple systems, with their intricate gravitational bonds, have a surprising resilience. The way the four stars in these systems interact creates a kind of stability that can withstand the turbulence of galactic mergers. In fact, some quadruple systems become even more tightly bound during these collisions, their orbits becoming more compact and their interactions more intense. This resilience provides astronomers with a rare opportunity to study the effects of galactic collisions up close. By observing how quadruple systems behave during these events, we can learn more about the dynamics of galaxy mergers and the forces that shape the universe on the largest scales. It's like having a front row seat to one of nature's most spectacular shows. Moreover, the survival of quadruple systems in such extreme environments challenges our understanding of stellar dynamics. These systems reveal how stars can adapt and even thrive in conditions that would seem unimaginably harsh. They remind us that the universe is full of surprises and that even in the midst of chaos, there's an underlying order and resilience waiting to be discovered. As we continue to study these systems, we're also uncovering their potential to influence the evolution of galaxies themselves. Quadruple systems can act as gravitational anchors during collisions, shaping the way galaxies merge and evolve over time. This adds another layer to our understanding of how the universe grows and changes, making these systems not just survivors of galactic collisions, but key players in the cosmic dance of creation and destruction. With this discovery in mind, let's move forward to explore the exotic chemical compositions found in some quadruple star systems, where the stars themselves hold clues to the universe's most ancient secrets. Shifting our focus to the chemical makeup of these cosmic wonders, let's explore quadruple star systems with exotic chemical compositions. These systems are like cosmic laboratories where the stars themselves hold clues to the universe's most ancient secrets. Unlike typical stars, which are primarily composed of hydrogen and helium, some quadruple systems contain stars with rare or unusual elements, offering a glimpse into their unique origins and histories. What makes these chemical compositions so fascinating is that they often hint at the stars' past interactions and environments. For example, some stars in these systems show unusually high levels of elements like carbon, oxygen, or even heavier metals. These elements, known as metals in astronomical terms, are typically forged in the intense heat of stellar cores or during explosive events like supernova. Their presence in quadruple systems suggests that these stars may have formed from material enriched by previous generations of stars, or that they've been influenced by nearby stellar explosions. One particularly intriguing example is a quadruple system where one of the stars has an unusually high concentration of lithium, a rare element that's often destroyed in the early stages of a star's life. This anomaly suggests that the star may have formed under unique conditions, possibly in a dense stellar nursery where interactions with other stars preserved its lithium content. Such discoveries challenge our understanding of star formation and the processes that shape stellar chemistry. Another compelling aspect of these systems is how their chemical compositions can reveal the history of their interactions. In some cases, stars in quadruple systems have exchanged material with one another, transferring elements from one star to another. This process, known as stellar cannibalism, can lead to stars with mixed or hybrid compositions, blending elements from different stages of stellar evolution. These interactions provide a window into the dynamic and ever-changing nature of multiple star systems. But the implications of these exotic compositions go beyond individual stars. They also offer insights into the broader history of the universe. By studying the chemical fingerprints of stars in quadruple systems, astronomers can trace the origins of the elements that make up our universe from the first stars to the present day. These systems act as cosmic time capsules, preserving the signatures of ancient stellar processes and helping us piece together the story of how the universe evolved. As we uncover more about these chemically unique stars, we're reminded of the vast diversity of the cosmos. Each system tells its own story, shaped by the forces of gravity, time, and the elements themselves. With this in mind, let's turn our attention to the final discovery in our journey, the future of quadruple star system research, where new technologies promise to unlock even more secrets of these fascinating cosmic ensembles. Turning our gaze toward the horizon of discovery, let's explore what lies ahead in the study of quadruple star systems. The future of this field is brimming with promise, as advancements in technology and innovative research methods are poised to revolutionize our understanding of these complex cosmic arrangements. One of the most exciting developments is the continued refinement of space telescopes and ground-based observatories. Instruments like the James Webb Space Telescope and upcoming projects such as the Extremely Large Telescope are set to provide unprecedented clarity and detail. These tools will allow astronomers to peer deeper into the hearts of quadruple systems, capturing intricate details of their orbits, interactions, and even their chemical compositions in ways that were previously impossible. Another groundbreaking area of research is the use of gravitational wave detectors, which have already transformed our understanding of binary star systems. As these detectors become more sensitive, they may soon unlock the secrets of quadruple systems, revealing the gravitational dances of 4 stars in motion. This could provide new insights into how these systems form, evolve, and eventually meet their fates. Artificial intelligence and machine learning are also playing an increasingly vital role in astronomy. These technologies are being used to sift through vast amounts of data, identifying patterns and anomalies that might otherwise go unnoticed. In the context of quadruple star systems, AI could help astronomers model complex gravitational interactions or predict the outcomes of stellar collisions and mergers. Despite these advancements, many questions remain unanswered. For instance, how do quadruple systems influence the formation of planets in their orbits? Could life exist on worlds bathed in the light of 4 stars? And what role do these systems play in the larger tapestry of galactic evolution? These mysteries continue to drive astronomers to push the boundaries of what we know. The future of quadruple star system research is not just about answering existing questions, but also about discovering new ones. Each breakthrough brings with it the potential to reshape our understanding of the universe, reminding us that the cosmos is a realm of endless wonder and discovery. As we stand on the cusp of these new frontiers, one thing is certain: the study of quadruple star systems will continue to illuminate the mysteries of the universe for generations to come. And with that, we conclude our journey through 50 strange and fascinating discoveries about these cosmic wonders, but the exploration doesn't end here. The universe is vast and its secrets are waiting to be uncovered. So keep looking up, and who knows what you might discover next. If you enjoyed this video, don't forget to like, subscribe, and hit the notification bell to stay updated on more fascinating journeys through the cosmos. Until next time, keep exploring. As we wrap up our journey through these 50 strange discoveries about quadruple star systems, it's clear just how much these cosmic arrangements challenge and expand our understanding of the universe. From the chaotic gravitational dances of 4 stars to the potential for habitable worlds orbiting multiple suns, each discovery reveals a new layer of complexity in the way stars and planets form, evolve, and interact. These systems are not just astronomical curiosities, they are windows into the fundamental processes that shape our cosmos. Quadruple star systems have taught us about the limits of gravity, the diversity of stellar evolution, and the potential for life in the most extreme environments. They remind us that the universe is far more intricate and surprising than we often imagine, and while we've uncovered so much, there's still so much more to learn. What other secrets do these systems hold? Could they help us answer some of the biggest questions about the origins of galaxies, the nature of time, or the possibility of life beyond Earth? As you reflect on these discoveries, let them inspire you to keep looking up and asking questions. The universe is full of wonders waiting to be explored, and every new observation brings us closer to understanding our place in the vast cosmic tapestry. If you've enjoyed this journey through the mysteries of quadruple star systems, be sure to like, subscribe, and hit the notification bell so you never miss an exploration of the cosmos. Until next time, keep your eyes on the stars and your curiosity alive. What will you discover next?